very fascinated about the magic wavelengths idea, I will mention a bit during my talk. So, the title today is the frequency ratio measurement at the 17th decimal place. These are the strong collaborators. So, Junye gave a very good introduction to the clock idea. So I have nothing to say, but our temporal goal is 10 to the minus 18 uncertainty, which means lose 1 second in this period. It's 2 times of the age of the universe. So, how to express frequencies? If the measurement precision is not so good, or down to 3 times 10 to the minus 16, SI unit is very convenient. What we measure frequency is that we measure the ratio, something divided by the CDM transition frequencies, and times this number. This is the definition of the SI second. But as June told that there are several clocks that achieve 10 to the minus 18 uncertainty. Then the question is how to express the frequencies. Then the frequency ratios between the good clock and good clock are the only means to express or compare physical quantities independent of the SI unit uncertainty. And my talk is to find and measure some meaningful quantities beyond the SI uncertainty, which is around 10 to the minus 16, which is to test the stability of constant. Or in the last part of my talk, I will give the application to geopotentiometry with atomic clocks. This is the history of the SI second. We are using the cesium clock as a SI second, which is realized with uncertainty of mid 10 to the minus 16. And our target is here at the level of 10 to the minus 17 or 18, which is not expressed by the SI unit. And in the long run, community expect the redefinition of a second in about 10 years. So I will talk about the Lattice clock, which is proposed in 2001. So if we believe in the constancy or fundamental constant, then the atomic clock would provide universal second. But we are pursuing this, whether constant is constant or not. So atomic clocks reference atomic ensembles to correct the oscillator frequency. And what we are doing is to find the good system for this atomic reference. For this purpose, we proposed optical lattice clock. So it was in 2001. We put the atoms in the optical lattice to eliminate collisions. And a good trick for the lattice clock, as Jun told already, is the elimination of the light shift perturbations by tuning the laser frequency to the magic frequency, which is given by this. By canceling out the light shift in the ground state and excited state, we can realize the nearly perturbation-free atomic frequency measurement. But in the last part of my talk, I will mention that this kind of very simple-minded strategy is not good enough to reach 1 times 10 to the minus 18 or below. New trick is necessary. So this is back to 1999 when I first visited Korea as a speaker. At that point, we are very excited about the efficient loading of strontium atom into a dipole trap because we wanted to make BC with strontium at this point. For this purpose, we calculate the right shift and the upper state at the point triple P1 and ground state singlet S0. And we try to find the optimum trapping wavelengths to efficiently load strontium atoms into the dipole trap. So this was the very origin of the magic wavelengths idea. So by doing so, we slightly improved the loading efficiency into a dipole trap. So that we were happy at that point. And in 2 years later, we tried the magic lattice spectroscopy with collaboration with Dr. Guido. And this was the first data for that. And by doing this experiment, we realized that the scalar state is really necessary to eliminate vector right shift as well as the tensor right shift. This was the story how we invented optical lattice clock. So now optical lattice clocks were studied worldwide. There are more than 20 groups in the world. And in particular, for strontium optical lattice clock, they have a good agreement between the clock measurement. And CIPM adopted the recommendation frequency for strontium optical lattice clock with this number. The good thing is that this number is only limited by the SI second uncertainty. So this is a good appeal for a need of a better definition of a new second. So to go beyond the SI second uncertainty, measuring the ratio of optical clocks are important. So this is the summary of these measurements. Up to mid 10 to the minus 16, cesium clocks are very effective. But beyond that, we need better optical clock. So the first measurement was done by Wineland's group in NIST, and we are doing these. Mercury-strontium ratio, ytterbium-strontium ratio at the level of 10 to the minus 17. And in the end of my talk, I will discuss strontium-strontium ratio for the application of geopotentiometry. So this is the outline of the talk. So the challenge for the clock is to access useful physical quantities as fast as possible. So first, I will address blackbody radiation issue for strontium, then present mercury-strontium, ytterbium-strontium ratio, and finally, I talk about geopotentiometry using distant strontium clocks. And also, I will mention how far can we push the lattice uncertainty down to, optimistically, 10 to the minus 19. So reduction of the blackbody radiation shift was a big concern for us. Optical lattice relies on Stark shift, but the Stark shift due to the blackbody radiation gives us uncertainty. When we proposed lattice clock, we thought the goal would be 10 to the minus 17. This is because of the blackbody radiation shift of 2 Hz at room temperature. I didn't imagine a very precise control as done by Junye at this point. So I thought that another strategy is to reduce the environmental temperature down to 100 K, for example. This is what we are doing now. So this is a dipole polarizability as a function of the frequency. At the 800 nanometer, 2 dipole polarizabilities becomes equal. By doing so, the right shift due to the dipole polarizability becomes the same and canceled out. This is the idea of the magic frequency. But the problem is the blackbody radiation shift at around 10 micron, which gives additional shift of 2 Hz at room temperature. But the thing is that this blackbody radiation energy is proportional to T to the 4. So by just decreasing the temperature down to 100 K, it's almost disappeared. We can reduce by a factor of 100 by doing so. This is what we are doing. For that purpose, we build 2 clocks on the same table because relativistic redshift is problematic in the long run. And we prepared a tiny chamber of a few cubic centimeters to put the atoms inside through a small hole. And we cool down the chamber by a Stirling refrigerator, which is also a very compact refrigerator, and reduce the blackbody radiation shift down to 10 millihertz level. So by changing the temperature from 100 K to 300 K, we measure the beautiful T to the 4 dependence. And by operating the 2 clocks at 95 K, we have a very good agreement between the 2 clocks, which agrees 1 times 10 to the minus 18. So we have a good reference to measure something else. So more clocks are needed to access physics. For example, by measuring the ratio with different atomic elements, then we can say something about the variation of fundamental constant. For example, we developed cryogenic Yb clock also. We use the same machine, but just we put the Yb metal to the oven. That's it. So it was quite easy. We can also reduce the blackbody radiation uncertainty down to 10 to the minus 19 level by using this cryogenic setup. This is how we measure, compare strontium clock and ytterbium clock with the frequency comp. What we are doing is measuring the ratio of vibration. Ytterbium vibrates 5 times 10 to the 14th in a second, and while the strontium vibrates 4 times 10 to the 14 in a second. From that, we measure the ratio with very good precision. Another trick we did is to drive ytterbium clock and strontium clock with the same laser. By doing so, the laser noise cancels out in the excitation probability of strontium and ytterbium. So we observe a very good correlation of the excitation probability. This reduces the laser noise contribution to the stability of comparison. By doing we say the synchronous comparison, we achieve this stability for 2-atom clock ratio. So we achieve 10 to the minus 18 within an hour, for example. And this is the result of the comparison compared to the previous measurement, which employs cesium clocks as a reference. We have a dramatic improvement in accuracy by referencing strontium clock. And we can describe the number with this 17 digit. This is slightly better than the previous ratio measurement done by NIST. So the thing is that current SI second is not good enough to express physical quantities. we did similar measurement using mercury atomic lattice clock. We measured this number with uncertainty of 8 times 10 to the minus 17. The good thing is that our clock can be compared with the recent Paris measurement. So our data are in agreement within the error bars. This is very good news for us. So the limiting factor is apparently the right shift, and we are doing effort to improve the uncertainty of lattice right shift. The time is quite limited. I will almost skip. But the thing is, at the 10 to the minus 18 level, even polarizability, electric dipole polarizability is not good enough to fully describe the right shift perturbation. Instead, we need a magnetic dipole or electric quadrupole interaction and also hyperpolarizability effect to describe the lattice right shift. But by managing these 1, 2, 3, 4 contributions, we expect we are able to achieve 10 to the minus 19. So this is a very complicated dependence on intensity by adding a multipolar effect and hyperpolarizability effect. But what we are thinking about is that this is the multipolar effect, and this one is the multipolar plus hyperpolarizability effect. These effects can be tuned by slightly detuning the lattice frequency in this way. By doing so, we can realize very small lattice uncertainty with a large intensity margin. By doing so, we hope to achieve 2 times 10 to the minus 19 in a few years. And we did a similar effort for ytterbium clock also. We are measuring hyperpolarizability effects for ytterbium and in the long run. And now we estimate the ytterbium lattice-related right shift to meet 10 to the minus 18. So we expect the ratio measurement at this level in the next experiment. So this is the final topic, geopotentiometry. So atomic clocks feels 10 to the minus 18 gravitational redshift by changing the height difference by 1 centimeter. Because we have a 10 to the minus 18 level clock, we can measure 1 centimeter in principle. So I call it quantum benchmark. This kind of monument will be replaced by optical clocks in the near future. In 20 years, 30 years, I hope so. So what we are doing is to compare clocks between Riken and University of Tokyo, which is 15 kilometers away. This is a very small spot in Japan island. We had 2 clocks at Riken and single clock at University of Tokyo, which uses the cryogenic clock. We asked the potential difference measurement for the Geoinformation Authority of Japan by using classical labeling measurement. And they bring gravimeter with them. So they can derive the gravitational potential difference between the University of Tokyo to Riken. In the meantime, we measure our clock shift by using 2 clocks at university and at Riken. And these blue circles are the clock result. The clock shift gives minus 700 millihertz. with uncertainty of 5 times 10 to the minus 18. And this red line is the leveling measurement, which has uncertainty of 5 millimeter. And last point, we ran a 3-day continuous measurement with an uptime of 73%. So 2 weekend clocks agrees very well 1 times 10 to the minus 18 because they're on the same optical table. But the frequency difference between the university and weekend was this number, 700 millihertz. So we determine the height difference with uncertainty of 5 centimeters. And in the long run, tidal oscillation will be observable by extending the distance between the fiber. This experiment again, we applied a synchronous interrogation of 2 clocks. We use the same clock to interrogate weekend clock and university clock to eliminate the noise of the laser frequency. As a result, we have a good correlation between the excitation probabilities for the 2 clocks. And this is the result. Without synchronous operation, we have this bad instability, but by using synchronous scheme, laser noise canceled out, and we have a 10-fold improvement in stability. And by further increasing the interrogation time of the clock, we expect the improvement of the stability. So in 6 hours, for example, we will achieve 10 to the minus 18 stability. Last 2 minutes. So clock will see tidal fluctuations. So the tidal fluctuation is huge. This is the calculation of the tidal perturbation at weekend, which gives us almost 6 times 10 to the minus 17 difference. But the thing is, at weekend and at University of Tokyo, this is very small area, just 15 kilometers away. So that this tidal perturbation cancels out down to 2 times 10 to the minus 19. So it's difficult to see. But if you take one of the clock to this area, Kyushu area, then the perturbation, tidal perturbation should be as large as 14 times 10 to the minus 18, which will be visible with optical lattice clocks. So the synchronous operation is quite effective for that kind of thing. We can use a remote clock with a mobile type, not so good clock, but by referencing a very good master laser stability. So we proposed optical lattice clocks simply by curiosity, but now it is becoming a tool to measure something useful. What is happening underground? For example, the change in magma chamber or cavity formation or something by networking optical lattice clocks in biofibers. 18 minutes, 80 seconds. So this is a great member we are working. In particular, Takamoto and Niels and Yamaguchi will be in the audience and ask them anything you have questions. So this is a summary. Thank you very much for your attention.
Thank you very much for this clear presentation. The paper is open for questions. Maybe I can start by asking the first question. So you mentioned that redefinition of the SI second that might be due to some time, and so we are going to have a global timescale 18 or the 10 to minus 18 level. But I would think that this only makes sense if we can also compare different clocks on different continents even. I mean, we've seen how to do this over fibers, but is there any idea out how you could do this between continents?
Yes, so it's a very good question, and for that purpose, I presented, for example, comparison between the university and region. Even in this small area, the comparison is quite difficult. We have, at that point, we need to rely on the measurement of leveling. But leveling also has a 5 millimeter uncertainty for that. So to share a global time is quite difficult. Instead of sharing a global time scale, we are observing the geopotential difference of their clocks. So the only way is to make a very good portable machine and compare at the institute and make an agreement. Or another way is to exchange the ratio of different atomic clocks. For example, if one determines strontium yttrium ratio at the level of 10 to the minus 18, and if that ratio is shared with different groups, I think that's good evidence that the clock is accurate at that level.
Yeah, probably that shows that the clock is accurate, but that wouldn't help to synchronize clocks.
Synchronize, yeah, yes. So for that synchronization, then the geopotential is a problem.
Okay.
So we will measure.
Any other questions? It's really hard to see. Well, if that's not the case, then let's thank Hidetoshi again.
Thank you very much.
And we move on to the next and final speaker of the session, which will be Mariana Savronova, and she will speak to us about searches for new physics using these fantastic new clocks.